Next speaker is Sreejato Bhattacharya. He will be giving a talk on efficient classical simulations of quantum query.
So we are interested in the query model of computation. So in this model, we have to evaluate a known function on an unknown input. So say the length of the unknown input is n bits. Let's represent the bits in +1 or -1. So the function is defined on a subset of +-1 power n. So it's a promise problem. So we know what the function is. The issue is we don't know the input. And second, we have the computational limits. Now, how do we access the inputs? We can ask an oracle queries of the form, give me the value of this coordinate, and the oracle will reply truthful. And the query complexity, denoted df, is the minimum number of queries needed to determine the function in the worst case. Again, we know what the function is, we just don't know what the input is. So, for example, one protocol would be you ask the oracle the value of x1, he says 1. Then you ask the oracle another value, he replies something. And suppose after 3 queries, you can determine what f of x is. So in this case, you needed to ask 3 queries. And the query complexity is the worst case over all possible inputs, the minimum number of queries needed to completely determine f. So this is the classical query complexity of a function. Now there is a quantum variant of this model. So by the way, and yes, these classical query algorithms can be naturally modeled as decision trees. For example, if your first query is query coordinate 1, then the root of the decision tree will be labeled 1. Then based on if your answer is -1, suppose you query coordinate 5, then the corresponding child will be labeled 5 and so on. And the values will be written on the leaves. So in other words, d of f is the minimum depth of a decision tree that correctly computes f on all inputs. Now we define a quantum variant of it. So again, the quantum query complexity model is defined as follows. We know what the function is, but we don't have full access to the input. So the input is given to us via quantum oracle. And how does that oracle act? So the oracle is a unitary operator, which is the tensor product of n single qubit operators. Now the ith operator does the following. If the ith coordinate of your input is -1, it flips the face of the ith qubit. And if the ith coordinate is +1, it keeps the ith qubit unchanged. So this is a unitary operator which encodes the input. Now the advantage here is that you can apply this operator to mixed states, which is essentially saying you can perform queries in superposition. So how do you define the quantum query complexity? So a quantum query algorithm is a sequence of operators where each operator is either this ux or some unitary operator that is independent of the input. And the cost of a protocol is the number of times you apply this operator ux. This is analogous to querying a coordinate in the classical model. And the requirement is that, so after all these operations, we perform a measurement with 2 possible outputs, let's say +1 and -1. And the requirement is that for every input in S, that is the set over which it is defined, the probability that the measurement outputs f of x is some constant, say 2/3. And here notice that the only randomness is over our quantum randomness from the measurement. There is no other randomness. So the cost of the protocol is the number of times we apply this operator ux. So to recall, there are 2 kinds of operators. One which is ux, that is provided to us. We don't know what x is, but we have access to this operator. And the other kind of operator is independent of x. So applying an operator ux is analogous to querying a coordinate in the classical. So it's easy to see that classical query algorithms can be simulated by quantum query algorithms. So the quantum query complexity is at most the classical query complexity. And the question we'll be interested is for various functions, how big can the gap be?
When you apply in the classical, you ask the bit and then decide.
Yes. Yes.
You apply
Yeah. So first of all,
you don't have any output from the defined, right?
yeah. So here there's a thing called principle of default measurement. So even if you are allowed general protocols of the form, apply some quantum operator, then measure something, then depending on the result of the measurement, do this thing or that thing. Suppose there was a protocol, then there is a principle called principle of default measurement, which essentially says that you can push all this measurement at the end. So it will not give you any extra power. So without loss of generality and with a very slight loss of parameters, we can assume we do only one measurement operation that there is no branching.
So seems to me that adaptiveness does not play a role.
So adaptiveness, yeah, I mean adaptive classical algorithms can be simulated by this form. Yes. So this is called the principle of default measurement. As in you can say your suppose your measurement was +1 or -1, then the next operator can specify if this qubit is 1, do something. If this qubit is -1, do something. And you can encode it in a single qubit operator. Oh yes, also there are some ancillary qubits as well. This is crucial. So we
Can I
can
say something?
Yeah.
Hello. Yeah. Yeah. I mean, just a small comment about that adaptiveness. Actually, to model classical adaptiveness, you have to add one more thing, which is usually not stated in the quantum literature, and that's actually a mistake. The thing is, you have to decide in superposition whether you want to query or not.
Yes.
Okay, so depending upon the state of maybe ancilla or other qubits in superposition, at time I, you have a choice of not querying or querying, and of course that query also is in superposition. The way I've defined it, at time I, you will query in superposition. You don't have the choice of not querying.
Oh.
Yeah. So the point is that most of the standard algorithms work in this restricted model where you always query at certain times, and most of the lower bounds work for the more general model where you have a choice of not querying.
Yes.
Okay, but I mean, this is a folklore in the community, but often not stated.
Okay, thank you for so with some extra things like ancillary qubits, we can assume this is the form of our quantum query algorithm. So let's define Q of F to be the minimum cost of a quantum query algorithm, which has this property that for every point where F is defined, the probability that the measurement outputs correctly is at least 2 by 3. Okay.
The cost is the number of times you are
Applying this operator UX, yes. So here are some examples. Let's consider the OR function. So the deterministic query complexity of OR is simply n, because whenever so OR is true if at least one of the coordinates is true, and it's false if all the coordinates are false. So the deterministic query complexity is always n, because you can assume that the oracle is answering adversarially. So whenever you query a coordinate, it answers false. So until you query the last coordinate, you don't know whether it's true or false. But the quantum query complexity of OR is theta square root, and this follows from Grover's algorithm. And there is a matching lower bound as well. Here's a function with a bigger gap. So the famous Bernstein-Fajjani problem can be modeled in this query model. So what's this? So assume that your function, suppose your bit length is 2 power k. So assume that string that you get is the truth table of some function. And suppose you have the promise that this truth table is the function which is actually inner product of x with a certain string, with a certain unknown string s. Now you can model it in several ways. I chose the following way to simply determine whether or not this function is non-zero. So using a quantum algorithm, you can just simply determine s using just one query. So the quantum query complexity of it is 1. But to actually check that, to actually retrieve each SI, you need a different query. So the classical query complexity of this is order k. So note that the gap between QF and DF here is unbounded. Like DF is not bounded by any single function of QF. So we look at the following thing. For what functions can we bound the gap between the quantum query complexity and classical query complexity? So,
This is a promise problem.
it is a promise problem because the promise is that the function is encoding the truth table of a function of this form. So the promise is this.
Promise. And it has a separation table for norm.
So we don't have such separation for non-promise problems. I'm going that we have a discussion that next time. So now let's look at the following question. For what kinds of functions do we have super polynomial separation between quantum and classical query complexity? So a classical result by Beals and Burman shows that if your function is not promised, that is, if it is defined on the entire hypercube, then there is no super polynomial separation between a classical and quantum query complexity. So given any quantum query algorithm for that problem, we can simulate it classically with a polynomial overhead. And actually, even this power 8 has been reduced further. I think currently it's 4.4 or something. But point is, it's never super polynomial. So, okay, so if the function is defined on the entire hypercube, there cannot be any super polynomial advantage. Now, what if the function is only defined on a constant fraction of the hypercube? Can there be a super polynomial advantage? And this is an open problem.
So how is the big? So that's a constructive algorithm. No?
Yes, yes.
So, something is going to go wrong with what I'm stating. Can you tell me what you have a quantum algorithm?
Yes.
No? It works only on the promise, but it possibly does something on the non-promise.
Yes. Yes.
Well, possibly it doesn't get 2/3, 1/3
Yes.
gap. But then I'm just going to run the same.
So, for if you want to run the Beals-Burman construction, it is crucial that the function's image misses a gap between it misses a gap between half minus epsilon and half.
Yeah, but it misses it on only the non.
No, but if you want to run this, if you want to do the Beals-Burman construction, it is crucial that fx does not lie in this interval for all x.
So somehow it uses it's going to.
Yes.
Okay.
Okay, so if you recall, what they do is that they find these minimal sensitive blocks, and they say these minimal sensitive blocks cannot be too high because then the block sensitivity at the other input is
other inputs.
yes, but you don't know that that other input belongs in H on your.
Yeah.
So Beals-Burman crucially uses the fact that the function is defined on the entire hypercube. So okay, what about promise functions that are defined only at a constant fraction of the hypercube? This is not known yet. And Beals-Burman's construction that I just mentioned crucially uses the fact that it is defined everywhere, and it's very non-robust in the sense that if the function is not defined even on a very small fraction of the hypercube, their proof, at least if you try to directly adapt their proof, it fails. So now the open problem that I'm going to discuss is the following. Suppose you have a function that is defined on a constant fraction of the hypercube. Can there be a super polynomial separation between its quantum and classical query complexity? And the conjecture is no. So now here's a basic fact. Suppose you have a quantum query algorithm making p queries. Now the final measurement that we make consider the probability of outputting 1 as a function of the input. Now it's known that this function can be represented as a degree 2t polynomial in the input, where t is the number of queries made. So the acceptance probability of any quantum query algorithm making a low number of queries is equal to a polynomial of low degree. And what structure do we know about the polynomial? It's that for any point in plus minus 1 power n, the output of the polynomial lies between 0 and 1. So to solve this problem, the following conjecture was made. The idea is that basically now forget the fact that this polynomial arises from a quantum query algorithm. Work for general polynomials instead. The only restriction is that for every point on plus minus 1 power n, the output of the polynomial lies in the interval 0, 1. So the conjecture is the following. Suppose I have any low degree polynomial of degree d, such that at every point in plus minus 1 power n, its output lies in the range 0, 1. Then given any epsilon, which will be the error parameter, I can find a decision tree of depth that is not too big, that is polynomial in d and 1 by epsilon, such that it approximates p up to L2 error at most epsilon. H square root epsilon. Yes. So this is the conjecture. This is a folklore conjecture. This has been made like 20 years ago. I don't know the first paper where it arises. So yes. Yes. So I'm going to discuss this conjecture now. Now, Aaronson and Ambainis gave a particular way to construct such a decision tree, which I'm going to discuss next. So Aaronson and Ambainis actually showed that the following conjecture implies this folklore conjecture, and this is known as the Aaronson and Ambainis conjecture. So now again, suppose you have a polynomial of degree d.
So what goes on if my polynomial t is just a constant half?
But in t is constant, huh?
Yeah, if the polynomial t is just a constant polynomial half,
Yes.
it satisfies the property that for every point of the hypercube.
Yes. And you can take t to be half, right? A t will always output. A t does not output 0 or 1, like t outputs 0.
Okay.
And suppose the polynomial don't take value in 0, 1 or the solid cube rather than Boolean cube, the answer from them.
So in any polynomial in plus minus 1 power n, you can assume it is multilinear because you can delete the high order terms. Now in a multilinear polynomial, the extremal values will always be achieved at the boundary. So if it is bounded on plus minus 1 power n, it's also bounded on the solid cube. Assuming it's multilinear, and you can assume it's multilinear because it will just reduce the cube. So here's now the conjecture. So you can assume without loss of generality these polynomials are multilinear. And the Aaronson and Ambainis conjecture states that if a function can be represented as a bounded function can be represented as a low degree polynomial, then it has a coordinate with very high influence. So I'm going to define influence next. So some review on Fourier analysis of Boolean functions. Any function from the Boolean hypercube can be uniquely represented as a multilinear polynomial, but these coefficients are called the Fourier coefficients. And the degree of the polynomial is simply the largest S such that the corresponding Fourier coefficient is non-zero. Now, the variance of the polynomial is simply suppose I sample a random point in uniformly randomly I sample a point in plus minus 1 power n and I output fx. What is the variance of this random variable? We call that to be the variance of f. And it has this simple expression in terms of its Fourier coefficients. And its influence of a coordinate I is the following. Suppose I randomly sample a point x and I flip the ith coordinate. By how much does f change? So it's the expectation of this quantity. And then it has this simple expression in terms of f's Fourier coefficients. And the total influence of f is defined to be the summation of the influence of all of its coordinates. So it's simply this. And what Aaronson and Ambainis conjecture states is that suppose your function has low degree and high variance, then one of its coordinates must have a very high influence. So if you look at this Fourier extension, it's clear that the influence is at least variance. There are other ways to see this also, like F-Einstein inequality. But it's clear that influence is at least variance. So from the definition of total influence, it follows that there is a coordinate whose influence is at least variance of f by n. But what Aaronson and Ambainis conjecture states that you can get a maximum lower bound on the maximum influence that is actually independent of n. It depends only on the degree and variance, and that too only polynomially. In fact, there is an inequality called O-triple-S inequality, which again says that if your function can be approximated by a decision tree, then it has an influence as well. So these two conjectures are actually equivalent. So this was not mentioned in Aaronson and Ambainis' original paper, but it has been seen there.
The OSS inequality, is it going to replace the n by the depth of the decision?
Yes.
That's exactly what.
Yes, so it was this inequality. Covariance of f of g is at least summation influence I of f times delta I of g.
Okay.
So yes, it replaces this by the depth. Yes. So these two conjectures are actually equivalent. Actually, Aaronson and Ambainis did not notice the other equivalence in their paper, but it's not very. So I'll actually give a sketch of the proof that if Aaronson and Ambainis conjecture implies the folklore conjecture. So if every coordinate, so if it is true that every high variance low degree function has an influential coordinate, then it also has an approximating decision tree. So here is a proof sketch. We have to design an efficient query algorithm for f. Now what do? Suppose at our current stage we have made t queries so far. So initially t equals to 0. Now let's say the restricted function is f subscript t. That means we have made t queries. We have queried coordinates I1 to IT, and we have gotten responses y1 to yt. Then ft is simply f restricted f with this restriction. That is, this is what we know about the function here.
The for all that is coming, the intentional or
Yes. So it's not true that as such the proof does not show that if f has an influential variable, then f has a decision tree. It shows that if all f with these properties have an influential variable, then all f with this property have a decision tree. So, okay, so here's the proof sketch. So we have given suppose this conjecture is true that if you have low degree and high variance, then you have high max influence. Now, given any such function, we have to construct a decision tree. So we consider the following query algorithm. Suppose we have made t queries so far. So initially t equals to 0. And suppose we have queried the coordinates I1 to IT, and we have gotten the responses y1 to yt. So let f subscript t denote f under this restriction. That is, this is what we know about f so far. So now here is our strategy. So first, we have already made too many queries. That is, if t is greater than threshold, threshold will be an appropriate polynomial function of g and 1 by epsilon that we shall choose later. And we have already exceeded these many queries, just output anything and terminate. The point is, this will have to be very low probability, so like output anything, not very far, output anything basically. Now suppose we haven't exceeded this threshold, so we haven't made too many queries yet. Now let's look at the variance of the restricted function. If the variance is too low, simply output the expectation of this restricted function. In this case, you can bound the error simply by second moment method. Since the variance is already low, so simply this expectation is a good approximation to the function. And now what if the variance is high? Then assuming the Aaronson and Ambainis conjecture is true, there exists a coordinate with high influence. So query this coordinate. And then go to the next step, like increase t by 1 and go to the next step. So again, if the variance is low, then outputting the expectation is a good approximation to the function. Now, and if the variance is high, we query an influential coordinate. So all that remains to show is that if we follow this strategy of querying an influential coordinate at each step until the variance goes too low, then we want to show that t does not exceed this threshold with high probability. So we want to upper bound the probability that the number of times we query exceeds threshold. Now, how do you do that? The intuition is the following. Let's look at the total influence of f subscript t. Now, on average, how much does it change? So suppose we query the coordinate I, but the influence of I is high enough. Now, there are two possibilities for the next function. It's either g, suppose g is the current function. Now, there are two possibilities for the next function. That is, either it's g restricted to xi set to 1 or g restricted to xi set to -1. So now suppose the input has been chosen at random. Then the response to xi will also be 1 and -1 with equal probability. So what is the expected value of the total influence of the next function? It's simply half of the total influences of these two functions. And the easy computation shows that this quantity is actually total influence of g minus the I influence of g. So what is happening is that on expectation, the total influence of my function is reducing significantly at each step. It's reducing significantly because I am assuming a lower bound on imply of g. So you should expect relatively quickly the total influence should drop. And since we already saw that variance is upper bounded by total influence, once we know that the total influence has dropped significantly, we also know that this is a low variance load. So we can simply output the expectation at each step. And therefore, the probability that we make too many queries, here the randomness is about the sampling of x, this is too small. So actually this can be easily formalized using martingales. So what we do is, suppose the input has been chosen uniformly at random, then consider the random variable which says what is your total influence of the function after time step t. Now this becomes a random variable. And then easy calculation shows that, so let yt denote this random variable, that is, what is the total influence of your function after time step t. Then the previous calculation shows that, and suppose alpha is the lower bound we get from the Aaronson and Ambainis conjecture. Then the previous slide, from the previous slide, it easily follows that this random variable forms a super-martingale. And then we can simply only capital T with that stopping time, that is when the total influence goes below this threshold. We have to upper bound the expected value of the stopping time. And for that, we simply use Doob's stopping time theorem. So just this is a super martingale, so the expectation that the stopping time is at most the initial expectation, that is influence of f, and influence is at most deeply. This is again easy to see from the Fourier expansion. So we get an upper bound on the expected stopping time. And here I assumed alpha is large enough. Like alpha is at least a polynomial in 1 by d and variance. This is actually therefore bounded by a polynomial in d and 1 by variance.
You also have a conceptual equality for d.
So like I think Azuma Hopkin will give you a concentration inequality here, because at each time step it's not changing by more than a certain quantity. But it's not really necessary in this context. So simply by Markov's inequality, we can upper bound the probability that it exceeds the threshold. So I have only 5 minutes remaining. I will just explain some of the works done recently. So the first surprising fact is that there does exist a lower bound on the max influence that does not depend on n. The first such lower bound was given by Dinoor, O'Donnell, Friedgut, and Kindler. And these are actually before the conjecture was made. But their max influence had a lower bound of 2 minus 3. And actually, they gave a junta for approximating f, not just a decision tree. So we have to convert this junta into an adaptive decision tree with polynomial f. I want to mention some of our results. So we showed the following last year. So for convenience, assume that the variance of f is some small constant, say 1 by 100. Now we showed the following result. Suppose you take any bounded function f. Now consider a random restriction of f, where the allied probability is order log d by d. Then with probability at least omega 1 by d, the random restriction will have an influential coordinate. So therefore, Aaronson and Ambainis conjecture will follow if you can show that the class of these low influence functions is mostly closed under random restrictions. That is, if you have a bounded low max influence function and you take a random restriction of it, with very high probability it will still not have any influential coordinates. If you can show this, Aaronson and Ambainis conjecture will follow. And I want to mention another recent work by Lovett and Zhang. So I want to mention another recent work by Lovett and Zhang in 2022. They gave a reformulation of Aaronson and Ambainis conjecture. This was using previous work by Tiller and Klein. So they showed the following. This conjecture is equivalent to Aaronson and Ambainis conjecture. That is, if you have a bounded low degree function, then we have a certificate. Then every point x has a sensitive block. That is, for every input x, you can find a small subset such that if you pick the coordinates in that subset, then the value of f changes significantly. And they showed that this statement is true for at least omega variance f of the. So this is the deformulation. We have to show this result is true for all inputs x. They managed to show that this result is true for omega variance of f fraction of the inputs. We were able to show that for omega 1 by d fraction of the inputs, there exists a sensitive block, but our blocks are more sensitive in that they are sensitive in the L2 sense and not in the L infinity sense. That is, if you take this block and you randomly reassign the coordinates in this block, you will deviate from the original point significantly. They said their result is that you deviate from the point at one particular assignment. We are saying you deviate from the point on expectation. And we believe there are some ways to strengthen this to the 99% regime. That is, so that for at least like 99% of the inputs there exists such a block.
What is x dot z that is on the block?
That is on the block where z is 1 flip x. So they showed this in the infinity sense that there exists a way of flipping the block. And they used some high dimensional concentration inequalities of Talagram. We used some completely different tools, just plain hypercontractivity. And we showed that these blocks, you don't need to flip a single input on expectation, they will be sensitive. And we believe there are some ways, we haven't found this yet, to extend this to the 99% magic. So, thank you.
What fraction of the inputs you managed to get that?
I got omega 1 by d, they got omega variance. Our flexion is slightly worse, but we have this extra strengthening that on average you are sensitive.
Wait, there is also a tail bound result.
No. That's, I mean, there is a tail bound.
Their hands on this one.
So they use a tail bound result of Talagram, that is like completely different.
No, so they don't have a previous step in which they show that for one various fraction of points, there's an average point nearby which also differs a lot. That's not what they show.
No, they show that there exists a block, there exists a point which differs a lot, but its distance is small. They don't know that there is a block such that if you randomly reassign the block, it will differ significantly. Like there is a infinity result, ours is a infinity.
Can you flash there? Yeah, so there exists a subset B. So you're saying that.
So I'm saying that there exists a subset B. That's it. If you randomly reassign.
Okay. So if you randomly.
Yeah, and they're saying
also there exists a subset B. Okay.
Yeah, and you're saying that only one assignment takes you to a further point. I am saying on expectation you go to a further point. And we use completely different tools. Our proof is very similar to Dinu's original proof.
Okay.
They use some concentration inequalities of Talagram and this notion of fractional block sensitivity. We use classical hypercontractivity. So it's giving this result. Suppose you have two subsets X and Y. So for any small thing. So they use this geometric inequality of.
These are classic parameters.
Yes. And they have some other notions they introduced in previous paper called fractional block sensitivity. Using that, they do this, and we prove this by just direct hypercontractivity, like following the steps of Beawood.
Other very general, but more related to the Green's Brownian simulation. So a lot of these things in quantum versus classical is we have it for partial functions, we don't have it for total functions and stuff. And one of the reasons is these simulation algorithms, not only if you want to actually find a solution on a particular input, you actually use these notions as blocks and other things to see how the algorithm works on nearby inputs or something, and that's where you don't have the quantum promiser. We don't have the promise over there, and you don't have. So, can we ask? Is there a study which works out what are those simulation algorithms which do not use the sort of going to nearby points, and are such simulation algorithms extremely weak?
So the only simulation algorithm I know is this whenever.
Okay. No, but is there even a way of trying to find out if an algorithm is not going to do this? It actually is very weak. It's a very strange way to result. But one of the reasons this whole promise versus total comes is because of the simulation algorithm running for these issues.
I don't know.
Okay.
So this is the only simulation algorithm I know. So, any more questions?